My name is Grace Pang, and welcome to the Interagency Modeling and Analysis Group pre-meeting webinar series for the conference on integrating machine learning with multiscale modeling. Our speaker for today is Dr. Stephen Lee from the Department of, and he will present on the advanced scientific computing research at the DOE. I'll pass it to you, Stephen. Thank you.
Okay, thank you, Grace. Yes, I'm with the Department of Energy, and I'm a program manager in the Applied Mathematics program, and also an acting research division director. And next slide. So just a quick outline for this 15-minute talk. In looking at the objective for this meeting, it resonated with what we're doing at the Office of Science in terms of integrating machine learning with multiscale modeling, especially for methods guided by fundamental principles in math and physics. Back in January of 2018, we had a workshop on the topic of scientific machine learning, and it generated a nice brochure and about a 100-page report. But the idea there is that scientific progress is being driven by three factors. One is massive data, simulations and networks. The second is the use of predictive models and adaptive algorithms, and also the use of heterogeneous high-performance computing. And the thought was that by putting a stronger foundation underneath scientific machine learning, what you could end up with is with better ways for humans and AI to collaborate to get science done. So that's what I'm going to summarize in this presentation this afternoon. So in the Department of Energy, we have 6 Office of Science programs. As mentioned, I am with the Advanced Scientific Computing Research Office, and in a nutshell, we develop enabling technologies for using basic research in applied mathematics and computer science to enable science across a wide range of areas. One of the offices is Basic Energy Sciences, which studies chemistry and material science. Another one that NIH is more closely affiliated with is BER, looking at biological and environmental research. And then there's 3 other offices. The Applied Mathematics program is in Oscar. And short story is that it's basically right now a $30 million a year program. It has about 50 projects based at labs, universities, and with nonprofits. Some main areas that we have are in core applied mathematics, which is, for example, optimization, linear algebra, uncertainty quantification, differential equations, and so on. We also develop the foundations for scientific software libraries. Some are well known, such as Pepsi and Trilinos, but we also have other codes as well. We have several large math centers that look at doing science at user facilities, such as light sources, looking at the power grid, additive manufacturing. And along the bottom there, you see some idea of some of the workshops that we've held over the years that are relevant to this webinar. We've had workshops on multiscale mathematics, analyzing petascale data, uncertainty quantification, running codes on extremely heterogeneous architectures such as GPUs and emerging technologies. But what I will emphasize in this webinar is the recent workshop that we had on using machine learning for science. So in preparing for this workshop in January of 2018, we did some homework in the sense that we had an organizing committee that at the end of 2017 put together a report that looked at machine learning through the lens of applied mathematics and scientific computing. And a short story again is that we do have a pre-workshop report that everyone read before coming to the workshop that was held in Bethesda, Maryland at the end of January 2018. So in the overall report that we have, we include this pre-workshop report and also some of the main findings that we had from the workshop. So in summary, what we identified from the workshop were 6 priority research directions. We call them PRDs, and 3 of them were foundational, and 3 of them were related to the different capabilities that were being used for machine learning. So what I'll do now is go through the 6 primary research directions. And the first one is the need for domain-aware scientific machine learning. When people are applying machine learning to their science problems, they want to include as much knowledge as possible in the approaches. So I won't read all the bullets and the picture, but the idea there is that with domain knowledge, you have some understanding of physical principles, symmetries, constraints, uncertainties about your problem. And if you can build those into your machine learning algorithms, that would be good. The second research direction, foundational, is related to interpretability. There's a need for not only getting results, but also being able to explain and understand them. So how do you balance the need between getting a result that seems correct versus understanding how the result was achieved? And this can be important, for example, when trying to debug a combined machine learning scientific simulation code that you're not just getting a result, but you have to have some physics built in so you can understand why it might be giving the results that it's giving. So the first 2 are close related, both domain knowledge and then interpretability that built in and understanding and being able to explain the results. The third part of the research direction is robust scientific machine learning. And you want to make sure that your results that you get from machine learning are accurate and stable. This goes towards making machine learning more mainstream. So right now, all the talk is about different types of machine learning, like deep learning and reinforcement learning, but 5-10 years down the road, it'll just be routine and very mainstream. So we want to help encourage that acceleration and adoption. So those were the 3 main foundational research directions that apply to all machine learning methods that we want to use for science: domain-aware, interpretable, and robust. In considering all the different ways that machine learning could be used for science, we identified 3 main use cases, and I will step through those now. So the 4th part of the research direction is for that first use case, and that's for data-intensive scientific machine learning. It's often the case that the scientist has a bunch of data, and they want to find the signal, pattern, or structure within that data. So there are tools like TensorFlow and other things out there that people can use. And that is really the first thing people often think of when they hear about using machine learning for science. The next one, use case number 2, is relevant to what this workshop is about. This is machine learning enhanced models and simulation. So using machine learning to build better surrogate models as part of a more complex scientific simulation, or using machine learning to identify better computational model parameters that are often chosen by expert knowledge, but machines can help perhaps adapt and learn those better. So if you look at the workshop report, this would be the main section that's most relevant to what the upcoming meeting is about. So the final and third use case related to complex systems. Using machine learning for intelligent automation, for decision support, for controlling complex systems. So you can think of cybersecurity, more resilient power grid, things along that line. It's what we call the outer loop. That you have some core problem that you're trying to solve, and you want to do some type of optimization, search computation, dealing with English problems, and things like that. So that gives a summary of the workshop report. Again, we looked at foundations and capabilities as shown on the left. For the 3 foundations, domain-aware, interpretable, and robust. And then for the capabilities that we are seeing that really spans the entire breadth of the DOE mission for analyzing data, for using machine learning coupled with simulations, and then controlling complex systems and doing some type of automation. So at the bottom there, you will see the URL for accessing the report and downloading them. So what follows on from that scientific workshop report is that we just had a update to the 2016 report that laid out a national AI research and development strategic plan. This is from NIDRD. And the update was basically that they had an eighth strategy that they added, expanding public-private partnerships. The way this workshop report showed up is in item number 2, strategy number 2, scientific machine learning is part of developing effective methods for human AI collaboration science. And also strategy 7, DOE is very interested in building a workforce of people who understand and can use machine learning for science. Also related, we have some AI for science town halls going on right now. There are 3 in July, August, and September. And then the 4th one is in DC right before the NIH meeting. So October 22nd and 23rd, in the second bullet, there's a Washington, DC town hall that looks at the way AI is being used for science and being organized by the DOE national labs. These are very big meetings with several hundred people. Invitation is required, invitation only. People can register. And the output from that town hall report will be another report to guide strategic planning at the labs in DOE. This slide from the DOE Applied Math perspective shows for those 3 major use cases that I had on the left, if you just look at the middle row about using machine learning to enhance scientific simulations, over the past 15 years or so, we had several funding opportunity announcements that went out to people at labs and universities for funding research that supports machine learning enhanced scientific simulation. So people who are doing multiscale mathematics research, we funded a lot of projects in that area back in 2005 through 2011. We also funded people with uncertainty quantification for doing machine learning and extreme scale science. But not only that, but the other areas, data-intensive science, machine learning, again, we supported research in that area since 2009, 2 years ago. And for the third use case, intelligent automation, again, past 2 years, we've been funding people to do that. So the short story there is that the pump is primed for people who want to look at the mathematical foundations for making a more robust, domain-aware, and interpretable machine learning approaches. And we really think that's a key enabler for doing science across the DOE mission. I'll just end with the last slide. The DOE Applied Math program has really laid the groundwork to harness both machine learning and artificial intelligence for scientific purposes. Again, these are being driven by data. I know that NIH collects a lot of data from its advanced instruments. Again, with this meeting coming up in a month, we're looking at predictive models and adaptive algorithms. And we want to run these on big machines and get results as accurately and quickly as possible. So I really do see that there's really changing the scientific method and the way we can use AI and machine learning to collaborate and get science done in a new, different, and possibly better way. Machine learning can offer insights into the way we're doing our multi-scale modeling. And you see some examples of what the exemplars are for scientific achievement that expand everything from high-energy physics to biology, chemistry, and so on. So again, the workshop report is listed at the bottom there, and there's a link that can be downloaded. Please be aware that there's a nice 4-page brochure that can be obtained from that link, but there's also a 109-page report for getting into the details and making this a good document to read ahead of time going into the NIH meeting October 24th and 25th.